All right, so let's go ahead and start with the skull. So we went over the skull a little bit last week, so this is a little bit of review. So right now we're looking at the anterior view, which is a view from the front. Okay, so let's start with the forehead bones. This is the frontal bone, the ridge of bone above the eyes. This is the supraorbital ridge. So remember orbits, those are the eye sockets. Supra means above. So ridge of bone above the orbits is the supraorbital ridge. Nose bones are nasal. Cheekbones are zygomatic bones. The bone where your upper teeth attach, that's called your maxilla. So from the anterior view, we have the frontal, we have the supraorbital ridge, we have the nasal bones, we have the zygomatic bones, and the maxilla. All right, so now we're going to turn the skull so we can see the lateral view. So from the lateral view, we can still see the zygomatic bone. The zygomatic arch will eventually be important when we're learning about human evolution, but this is the zygomatic bone. The bone that's right by your ears, this is the temporal bone. So think temples, temporal. So superior to, right above the temporal bone, we have the parietal, and we have the frontal. And we can still see the nasal bones here from the lateral view as well. And that bump, everybody feel behind your ears, that bump right behind your ears, that's the mastoid process. All right, so now we're turning the skull so we can see it from the posterior view. So from the posterior view, we've got the occipital bone. And then superior to it, right above it, we've got the two parietal bones here. Okay, and then from a superior view, so looking at the skull from above, we can see the two parietal bones, and we can also see the frontal. And this suture running down the middle here, this is the sagittal suture. We'll eventually be learning about the sagittal crest, but it is important to know that the sagittal suture is what runs down the middle and it separates the two parietal bones here. Okay? All right, so one more time from the front, we've got the frontal bone, supraorbital ridge, nasal bones, zygomatic bones are the cheekbones, and the maxilla here. From the lateral view, you can still see the zygomatic bones. We've got the temporal, so think temples, temporal. We can see the parietal. We can still see the frontal and the nasal. Bump behind the ears, mastoid process. From the rear, from the posterior view, we can see the occipital bone. And we can see both parietal bones. From the superior view, we can see the parietals and the frontal. Okay, so there's the skull. And then your jawbone, so this is your mandible. So your chin is the mandibular synthesis. So that's a feature that's unique to humans. Everybody feel your chin. We have what we call a protruding mandibular synthesis. Some of our ancestors will have either vertical or receding. And this part here is the ramus. And then when you're looking at the dentition, so for dental formula, for modern humans, this is something we share with our ancestors and also with the great and lesser apes. We have a 2-1, 2-3 dental formula. So remember the way we count dental formula, we're going to divide the jaw in half, essentially dividing the whole mouth into quadrants. So in each quadrant, we start from the front. We count 2 incisors, 1 canine, 2 premolars, and 3 molars. So that's where we get the 2-1, 2-3 dental formula. And if you've had your wisdom teeth removed, then your actual dental formula is 2-1, 2-2, since you only have 2 of your molars. Okay, so mandibular synthesis, that's your chin. Ramus. Dental formula, you start in the front. You're counting incisors versus canine. So 2 incisors, 1 canine, 2 premolars, and 3 molars. Okay? All right, so next one we're going to focus on is the femur. So the femur is your thigh bone. So easiest way to side a femur is we have to know that the front of the femur is going to be smooth. So the anterior view is smoother. The posterior end is going to have this ridge along the back called the linea aspera. which will be important when we're learning about bipedal adaptations. Bipedal hominins have this linea aspera, whereas quadrupedal apes, like a chimpanzee, has more of a smooth posterior femur. Okay, so at the proximal end, so when you're talking about long bones, we'll talk about proximal end versus distal. So proximal is closer to your core, closer to your body, and then distal, think distance. So distal is farther away. So at the proximal end, so this is the end that is going to articulate with your pelvis. So the head of the femur will articulate with the ossitabellum of your innominate bone. Okay, the innominate bone is part of your pelvis. Okay, so your pelvis articulates like this. So you've got your two innominate bones, or os coxae. So the head of the femur will articulate with the ossitabellum. Okay, so that's the proximal end. So at the proximal end, you can see the head of the femur. This bump here, this is the greater trochanter. And then the smaller bump, that's the lesser trochanter. So we've got head of the femur, greater trochanter, lesser trochanter. All right, then down here at the distal end, so remember distance farther away from the body. So we've got the two condyles. So the condyle that's closer to your midline, that's the medial condyle. And then the one that's closer to your side, that's the lateral condyle. Okay, so this is where your femur will articulate with your tibia. So your tibia is your shin bone, so it will articulate like this. So the word articulate just means to touch. Okay, so with your femur, important aspects, you have to remember that the front side is the smooth side. The anterior side is smooth. The posterior view is going to have this ridge along the back called the linea aspera. At the proximal end, we have the head of the femur that articulates with the ossitabellum of your innominate bones, and your greater trochanter, lesser trochanter. Okay? All right. Next bone we're going to focus on is your pelvis. So the reason we're focusing so much on the skull, the femur, and the pelvis, these are the bones that are going to be really important when we go through the human evolution chapters, understanding bipedal locomotion, adaptations for bipedal locomotion. And then with the skull, we need to understand how the skull changed as cranial capacity expanded. And you know, aspects of our skull are going to change as we look at the progression of human evolution. All right, so with our pelvis, so when it's articulated, it's going to look like this. And I don't have enough hands, but envision in the back here, in the posterior, there's going to be the sacrum and coccyx. Okay, but right now we have the two innominate bones, or os coxae, articulated. So each innominate bone is going to be made up of three fused bones. So the top is called the ilium. So this crest right here, when you feel the top of your hip, that what protrusion you can feel, that's the iliac crest. But this entire portion, this is the ilium. Bottom half is the ischium. Way I was taught to remember it, ischium kind of sounds like tushy. So, you know, I know it's kind of silly, but if you remember, ilium is the top half, bottom half is the ischium. And then where it articulates with the other innominate bone, that's the pubis. So three fused bones, ilium, ischium, and pubis. And then if you're looking at this all articulated together, if you envision the sacrum and coccyx here in the back, this entire structure is called the pelvic girdle. Okay, so this pelvic girdle is from a male. So in chapter 7, next week, when we start learning about forensics, you're going to learn how to determine whether you're looking at a male or a female. So the aspects you're going to look for, easiest way to tell, in my opinion, this notch here, this is called the greater sciatic notch. If it's difficult to fit your wrist in it, see how there's a gap there? If it's difficult to fit your wrist in, you're likely looking at a male. And if it's really easy to fit your wrist in, you're likely looking at a female. Okay, so for a female, she would have a wider, greater sciatic notch. What that does is it pulls back the sacrum and coccyx to widen the birth canal. Okay, so males would have a narrow, greater sciatic notch, females have a wider. Other part you're going to look at when you're determining male versus female is the sub-pubic angle. So for a male, it's going to be relatively narrow. For a female, it's going to be much wider. So again, opening up that birth canal. And then when you look at it from a superior view like this, So again, envision the sacrum here in the back. So a male will have a relatively narrow pelvic inlet, whereas the female will be much wider. Okay? All right, so let's talk about, let's do the foot. All right, so here's the foot, your heel bone. This is the calcaneus. Heel bone is calcaneus. This bone here is the talus. Okay, so the talus will articulate with your tibia.
I have a quick question about the hip portion that you were talking about. Sorry. So
no, go ahead.
You said that you showed the difference between male and female. Is that generally true for most animals? I'm guessing it is for primates.
For primates, it's true. I mean, so especially for humans, because humans have expanded cranial capacity, we have essentially larger brained babies that are passing through our birth canal. Mm-hmm. Childbirth for an ape, like a chimpanzee, gorilla, orangutan, it's not as dangerous or complicated, partially because they're quadrupedal. So being quadrupedal doesn't require this pelvis that allows for upright walking. One of the kind of evolutionary trade-offs that goes along with upright walking is our pelvis had to become relatively more narrow. But that obviously caused some complications with birth. But that's true. I can say it's true for apes. I mean, I'm not necessarily an expert in any anatomy except for humans and apes. So I would have to look into that to determine whether that's true for all mammals. But I can tell you it's true for humans and the great apes.
Okay, thank you.
Sure, of course. All right, so, sorry guys, I've got bones spread out all over, so I'm trying to find the right bone. All right, here we go. Okay, so the talus, so we're looking at the bones in the foot. So we have the heel, which is the calcaneus. This is the talus here. So the talus will articulate with your tibia, with your shin bone. Okay. Oh, and I got the wrong tibia here. There we go. All right, so when you feel the inside of your ankle, what you're actually feeling is the medial malleolus of your tibia. So everybody feel the inside of your ankle? That bump is actually not your ankle, it's the distal end of your tibia, which we call the medial malleolus. Okay, and then when you feel the outside of your ankle, you're feeling the distal end of your fibula. Okay, so in the foot, so we got the heel, which is the calcaneus. This bone here is the talus. The bones in our ankle, those are called tarsal bones. The bones in your foot, these are called metatarsals. And then the bones in your toes, those are called phalanges. Okay, so they distinguish on the rows of phalanges, the row that is closest to your metatarsals, so closer to the core of your body. These are the proximal phalanges. The row in the middle is the intermediate phalanges, and then those that are farthest away, so farther away distance, those are distal phalanges here. So your big toe only has the proximal phalange and the distal phalange. Okay, but the others have 3 rows. All right, so in the foot, we've got the heel, which is calcaneus. The talus articulates with the distal end of your tibia, of your shin bone. So when you're feeling that bump on the inside of your heel, that's the medial malleolus of your tibia. Bones in our ankles, those are tarsal bones. Bones in your foot, these are metatarsals. Row of phalanges closest to the metatarsals are the proximal phalanges. The middle row, intermediate phalanges. Farthest row, distal phalanges. Okay? All right, so your tibia will articulate at the proximal end. At the proximal end, your tibia articulates with your femur, and then your patella is also going to go here. Your patella is your kneecap. Okay, so if you know anybody that's ever had a knee replacement, what they usually do, they're replacing the patella, and they also sometimes have to shave down part of the femur and the tibia where it articulates, and they're putting in a new joint there. Okay, so where it articulates with the femur, we've got the condyles again. So it's the lateral and the medial condyles. If you feel that bump that's right below your knee, that's the tibial tuberosity. You got the tibial tuberosity. And then this crest, so anybody that's ever hit their shin on something hard, it hurts really bad. This ridge right here is called the anterior crest. Okay, so this bump right below your knee, you've got the tibial tuberosity. This part here on the anterior view, that you can see from the anterior view of your tibia, this is your anterior crest. And then down here at the distal end is where your tibia will articulate with your talus, which is part of your ankle. So this bump that you feel on the inside, that's the medial malleolus here, medial malleolus. So when you feel the inside of your ankle, what you're actually feeling, that bump is the medial malleolus of the tibia. All right. All right, let's talk about our arms. Sorry guys, I know I'm kind of going in random order here because I've got bones spread out all over. All right, so this is our humerus. So in your arm, the long bone in your upper arm is called the humerus. So at the proximal end, the head of your humerus will articulate with the scapula. Okay, so here's your scapula here. This is the scapular spine. We're looking at the posterior view right now. This is the scapular spine. So the humerus will articulate with the glenoid fossa of the scapula. Okay, head of the humerus articulates with glenoid fossa. And down here at the distal end, you've got the oscillarian fossa. So this is where it will articulate with the ulna. So easiest way to determine ulna versus radius. So in your lower arm, you have two bones. You've got the ulna and the radius. So when you look at the proximal end of the ulna, so this is the end that's articulating with your humerus, the proximal end of the ulna has this U shape that's called the oscillarian process. Okay, so the oscillarian process is going to articulate with the oscillarian of the humerus, oscillarian fossa. All right, so your humerus and your ulna articulate like this. There's your different views there. Okay, so upper arm you have the humerus, lower arm you've got radius and ulna. Easiest way to distinguish the two, at the proximal end of the ulna, there's this U shape, the oscillarian process. At the proximal end of the radius, you have this circular shape here. So when you look at the circular shape, this is the head of the radius at the proximal end. So you've got this circular shape here that's articulating with the humerus. So when you hear the phrase, hit your funny bone, what you're actually usually hitting is the proximal end of your ulna. Yes, question?
Yeah, and I was just going to say something else I was told that's a good way to remember, that if you see a skeleton in anatomical position, radius is to the right. So I always remember that R and R.
Yes. Yeah, so if you're thinking anatomical position,
Yep.
so remember you're standing up like this, thumbs are out. So what you're feeling, when you feel the inside of your arm here, that's the ulna. And then to the right, you've got your radius here. Okay, so when you're looking at your arm like this bone here, that's your ulna. This bone here, that's the radius. So the radius is also allowing you to do this motion, which is what they call pronating. Okay, so think about the radius is allowing you to do this motion, and then ulna is more responsible for this motion here. All right, questions so far? You guys are good? Okay. All right, so let's talk about the hand. All right, so kind of like tarsals, the bones in our wrist, these are called carpals. So the way I remember it, if you have carpal tunnel, then your wrists hurt. So that's affecting your carpal bones. Okay, so kind of like metatarsal, the bones in our hand are called metacarpal. So the metacarpal bones are going to articulate with your carpals. Okay, and then bones in your fingers are also called phalanges. So that's the same name for your toe bones. So toe bones and finger bones are called the same thing. The row of phalanges that articulates with the metacarpals, these are the proximal phalanges. Remember, proximal, closer to the core of your body. So these are your proximal phalanges. The middle row, those are the intermediate phalanges. And then your fingertips, those are your distal phalanges. Remember, distal, farther away from the core of your body. Distal, distance. Okay, and your thumb, kind of like your big toe, your thumb only has 2 rows. So your thumb has the proximal phalanges and the distal phalanges here. Okay, so in the hand, we've got carpals, we've got metacarpals, proximal row of phalanges, intermediate row of phalanges, and then distal row of phalanges. All right, how you guys doing so far?
Good.
You guys good?
Good.
Good.
Okay, so I only have a lumbar vertebrae. So the lumbar vertebrae, the vertebral column is also an important aspect that we need to learn about to understand bipedal locomotion. It'll keep coming up in future chapters. So for humans, for bipedal hominins, our lumbar vertebrae, so those in our lower back, are going to be the largest. They're going to have the largest circumference here because they're supporting the most body weight. So the vertebrae in your neck, those are called cervical vertebrae. So if you think about if you need a cervical collar, it goes around your neck. So cervical vertebrae in our neck. In our mid region, those are thoracic vertebrae. And then in our lower back, these are lumbar vertebrae. So if you think about if you go shopping for a car or furniture, they talk about lumbar support. What they're talking about is that part of the chair or the car seat that's supporting your lower back. You could also argue that humans are not necessarily perfectly adapted to bipedal locomotion even in modern day, because lower back pain is still one of the #1 reasons why a human would visit a general practitioner. And sometimes as well, it's right where the lumbar vertebrae start to curve in with your thoracic vertebrae. That's where a lot of humans end up with lower back pain or mid back pain, and they're, once you hit your 50s and above. Okay, so the biggest are the lumbar vertebrae. And then
I actually had a quick question about that. When it comes to evolution and how we started walking upright, and because I've known about our spine isn't very adequate. So
right.
It's kind of like, well, why did we even start walking upright if it's not necessarily like benefiting us in any way?
Well, in our evolutionary past, the benefits would have been, of course, there's tons of theories on this, but the benefits would have been being able to stand upright to allow you to see longer distances. Also, standing upright frees up your hands, which allows you to use and make tools, carry babies, et cetera, et cetera.
Right.
Being upright is also sometimes considered to be more, it has a benefit as far as thermoregulation goes. If you envision, being out on the African savanna, if you're quadrupedal, that hot sun is hitting your entire back, your head, your entire back. But if you're bipedal, it's really only hitting the top of your head, which is, what many theorize we still have hair on our head, but not necessarily on the rest of our body. We still have hair on the rest of our body, not as, it's not as thick as the hair on our head, essentially. So the hair on your head is helping to give you protection from UV radiation from the sun, and also helps with thermoregulation. But we've also lost our body hair for thermoregulation in the sense of sweating, because sweating is the #1 thing that we have above the other mammals, because we can sweat and evaporatively cool our bodies. It's not actually the sweat that cools you down, it's the process of your skin getting damp and then evaporating is actually what helps you cool down. So that's one advantage that humans have over other mammals, because we have that ability to evaporatively cool. In our evolutionary past, it really was, we learned about adaptive radiation in lab #4. We learned about, the process of the 4 forces of evolution, adaptive radiation, and making sure that we're not competing with too many organisms at the same time. So if you envision that we still, here in modern day, we still have apes, we have humans, the apes were remaining more quadrupedal and adapted to living in the forest, whereas humans eventually adapted to being more bipedal and living more on the African savanna. But in the very beginning, humans, bipedal humans, were still living in the forest, and we'll learn about that. That's one of those theories that has changed over the years. It used to be believed that, you know, once bipedalism emerged, we almost immediately started moving out on the savanna. But actually, the earliest bipedal hominins, like Ardipithecus ramidus and even the Australopithecines, were predominantly living in a forested environment. So early on, we're going to see what we call a very mosaic anatomy. So there's going to be aspects of their skeleton that are more like quadrupeds and other aspects that are more like bipeds. Like, for example, Ardipithecus has a pelvis. The top half looks more like a biped pelvis. Bottom half looks more like a quadruped. Ardipithecus also has some features like they have retained an opposable hallux. You know, we have an opposable thumb, but chimpanzee and Ardipithecus, they're going to have an opposable hallux, opposable big toe. So that's a retention of some of those arboreal skills. Also, their fingers, their phalanges, and their toe bones are going to be somewhat longer and more curved early on. So, I mean, the quick answer to that question is that we didn't necessarily evolve to be bipedal overnight. It was a process that has taken 6 million years. And, you know, the original advantageous aspects would be to reduce competition. You know, we're not in direct competition with quadrupedal apes. If we become bipedal and more terrestrial, it frees up our hands for using tools, making tools, and carrying babies. It's possibly more, there's benefits for thermoregulation. There's benefits for seeing over, you know, eventually once we did move out in the savanna, there's benefits for seeing over taller grasses. But we will definitely go into this in much more depth when we go into chapter 14. Chapter 14 looks exclusively at the evolution of bipedalism. Chapter 15 will look at the Australopithecines and early members of our genus Homo. And then chapter 16 focuses in on basically Homo erectus and onwards. So even though bipedalism emerged 6 million years ago, you don't really see a commitment to bipedal locomotion until you get to Homo erectus. And in those very early bipeds, you're seeing a very mosaic anatomy, mixed anatomy that's indicating they did both, that they were quadrupedal when in the forest and bipedal when on the ground. Okay. Does that somewhat answer your question so far?
Yeah, no, I've just always found it interesting because it seems like monkeys are so much stronger than us, but yet we're smarter, and it's confusing why.
Yeah, I mean, there's definitely, and we'll talk about that too. There's certainly some benefits to quadrupedalism. There's certainly, you know, they can get through the forest much quicker than we can. They're obviously much better climbers and brachiators than we are. So there's certainly, you know, there's certainly some benefits that they have over us. But I think the biggest thing, like for me, that kind of clicked, that made sense, is we can't have too many organisms that are trying to occupy the same environmental niche. And to me, in my mind, that's probably what happened at that point in our evolutionary history, because we split from the other apes somewhere between 5 to 7 million years ago. So there must have been some sort of environmental pressure at that point in time that there were too many organisms that were trying to fill that same role. So it made sense for adaptive radiation to occur. So thinking about, you know, this branch, you know, pongodids, the apes continue to go in this direction, and then hominins, our bipedal ancestors went off in this direction. So in reality, that's beneficial for both, because now they're not in direct competition with one another.
Right. Okay. Well, thank you.
Yeah, of course. And stay tuned on that. We're going to go definitely more in depth on that. But this chapter, you know, the way I look at this chapter, I mean, I'm not going to make you guys memorize every single aspect of the bone like you would in an anatomy class, except for the skull, femur, and pelvis. Okay. Because those are the part of the skeleton those parts are going to be critical for understanding human evolution. I mean, I want you to understand the other bones and know the basics of how to identify them and how they articulate. But the bones I really want you to focus on are the skull, the femur, and the pelvis. Okay. Does that sound like a fair deal?
Yes, sounds great.
Yes. Okay. All right. So how about, unless there's any other questions, how about we go over the skull, femur, and pelvis one more time? Just to make sure we're all really comfortable with it. Sound like a plan?
Yes, please.
Sounds good.
All right. Perfect. All right. So we're looking at the skull. And actually, let me try turning this light out and see if it's better, because I don't know. That's probably worse, actually. Sorry, I keep trying different rooms to see what room is going to be the best for looking at the skull, but we'll keep working on it.
It's more.
All right,
It's
so looking
when
at,
you turned off the light, it was shinier on the skull. So this is better.
okay. Yeah, I think that with the light is probably better, but let me turn the fan off now. All right, so now we're looking at the anterior view, so a view from the front. So forehead bone. And I encourage you guys that you guys are on mute, so at home, go ahead and say this stuff out loud. I know I won't be able to hear you, but at least that's the way I learned it, guys, just saying the names of these out loud over and over and over again. It really does help kind of solidify it in your mind. So go ahead and say them out loud with me. So your forehead bone is going to be the frontal bone. Forehead bone is the frontal bone. The ridge of bone that is directly above the eye sockets, directly above the orbits, this is the supraorbital ridge. So one more time, the ridge of bone directly above the orbits, this is the supraorbital ridge. The eye sockets, these are orbits. Nose bones are nasal. Cheekbones are zygomatic. Cheekbones are zygomatic. The bone where your upper teeth attach, this is your maxilla. So from the lateral view, the bone that is by our ears, so think temples, temporal. The bone by our ears is temporal. The bone that's superior to, so right above, this is the parietal. And then we've got the frontal here. We can still see the zygomatic. So eventually we'll be learning about the zygomatic arch. We're going to look at the arch of this bone here. So that's the zygomatic bone. The bump behind your ear, this is the mastoid process. Okay, so from the lateral view, we can still see the maxilla. We can see the nasal bones. You can see the frontal. Bone by our ears is the temporal. Right above, superior to the temporal, we've got the parietal. Bump behind our ears, mastoid process. From the posterior view, we can see the occipital. This is the occipital bone. And then superior to the occipital, we've got the two parietals. Okay, and the suture that's running down the middle, that's the sagittal suture. Okay? All right, superior view, so a view from above, we can see the frontal bone, and we can see both parietals here. Okay, so one more time from the front, frontal bone, supraorbital ridge, orbits, nasal bone, maxilla, zygomatic. From the lateral view, from the side, we can still see the maxilla, we can see the nasal bones, we can see the frontal, we can see the zygomatic bone, the cheekbone. Bone by our ears is the temporal. And then superior to the temporal, we've got the parietal. The bump behind our ears, mastoid process. The hole for our ears, auditory medius. Auditory medius. From the posterior view, we have the occipital, parietals. From the superior view, we can see the frontal and both parietals. Okay, and then our mandible, our jaw. So this entire structure is called the mandible. Our chin is the mandibular synthesis. So remember, for humans, humans are the only hominin species that have a protruding mandibular synthesis. And this part here is the ramus. And then when we're looking at our dentition, so dental formula 2, 1, 2, 3. So we're going to divide the mandible in half. So we're going to start at the front. So the anterior dentition are your incisors and canines. So on each half, we'll have 2 incisors and 1 canine. So that's where the 2, 1 comes from. And then your posterior dentition is your premolars and your molars. So we have 2 premolars and 3 molars. Okay, so our dental formula, starting from the front, 2 incisors, 1 canine, 2 premolars, and 3 molars. So that's where the 2, 1, 2, 3 comes from. Okay. All right, that's the mandible. All right, looking at the femur. So aspects of the femur, we need to remember that the anterior portion, the front side of the femur is going to be smoother, and then the back, the posterior, is going to be rougher because we have this feature called the linea aspera, which is going to be important when we learn about bipedal locomotion. It's where the muscles and tendons attach for bipedal walking, running, and jogging. But for now, just know that this ridge along the back is called the linea aspera. So here at the proximal end, so remember proximal is this end that is closer to the attachment to your body. All right, so at the proximal end, the head of the femur is going to articulate, is going to touch the ossitabellum. So it's this ball socket joint here, the ossitabellum of your innominate bone. So if you know anybody that's ever broken their hip, generally what happens when you break your hip, you're not actually breaking the innominate bone. What you're breaking is the neck of your femur here, okay? All right, so your head of your femur articulates with the ossitabellum of the pelvis. Okay, larger bump here. This is the greater trochanter. Smaller bump, that's the lesser trochanter. All right, and then down here at the distal end, where the femur articulates with the tibia, we've got the medial condyle and the lateral condyle. This is where your femur articulates with your tibia, with your shin bone. Okay, so at the proximal end, your femur articulates with the ossitabellum. At the distal end, the femur articulates with your tibia and also your patella. That's your kneecap that would go here. Okay, the bones of the pelvis. Let's see if I can actually get this sacrum to articulate here for you guys. Wish I had more hands here. No, I don't think this will work. All right, so pelvis. Remember the entire structure. Envision that the sacrum is in the back for me. But this entire structure, the two innominate bones plus the sacrum, entire structure is called the pelvic girdle. Okay, so the pelvic girdle is made up of the two innominate bones and then your fused vertebrae, your sacrum, and your coccyx here. Because this is at the bottom of your vertebral column. So your vertebral column, you have your cervical vertebrae, then your thoracic, then your lumbar, and then the fused vertebrae are your sacrum and coccyx. Okay, so the entire pelvic girdle, the three bones, the two innominates, plus the sacrum and coccyx. So then when you're looking at each half of it, so this bone here is either called the innominate or os coxae. I know it's confusing. They have two names for it. I just don't want it to confuse you if you see it called different things. Some books call it innominate, some call it os coxa or os coxae. So the top half is the ilium. Bottom half is the ischium. So think ischium, tushy. And then where it articulates with the other innominate bone, this is the pubis here. So these are three fused bones, the ilium, the ischium, and the pubis. This crest here at the top, so when you feel the top of your hips, what you're feeling is the iliac crest. And then this notch here, so when you're looking at the lateral view, a view from the side, this notch is the greater sciatic notch. So that'll become important in lab 7 when we're learning how to determine male versus female. And the easiest way, at least in my opinion, I know you guys will be able to actually pick up the bones, but if you have a narrow greater sciatic notch, it's going to be difficult to fit your wrist in. So see how there's an opening there. So this is a male pelvis. So a narrow greater sciatic notch. Other aspects you're going to look for, sub-pubic angle. So it's relatively narrow for a male. It's going to be wider for a female. And then also when you flip it over like this, again, envision that the sacrum is in the back there. But the pelvic inlet, so essentially the birth canal, the pelvic inlet is going to be relatively narrow for a male, and it's going to be much wider for a female to allow for childbirth. But for bipedal hominins, childbirth is sometimes dangerous and complicated because we have that evolutionary trade-off of a overall narrow pelvis in comparison to a chimpanzee, for example. Okay, bones of the hand. We got a hand right here. The bones in the hand. So our wrist bones are called carpal. So remember the way I remember it, if you got carpal tunnel, your wrists hurt. So the bones in your wrist are the carpal bones. The bones in your hands are metacarpal. The bones in your fingers are called phalanges. So the row of phalanges that are closest to your metacarpals, these are the proximal row of phalanges. The row in the middle, intermediate row of phalanges, and then those in your fingertips, distal row of phalanges. So remember, in your thumb, you just have the metacarpal, the proximal phalange, and the distal phalange. Okay. Bones in your foot. So your heel bone, this is the calcaneus. This is the talus. So the talus is the bone that articulates with your tibia. Remember, your tibia is your shin bone. So when you're feeling the inside of your ankle, what you're actually feeling, that's the medial malleolus that's on the proximal end of your tibia. Okay, so you've got the talus, the bones in your ankle. These are called your tarsal bones. Tarsal bones. The bones in your foot, these are the metatarsals. The row of phalanges that are closest to your metatarsals, these are the proximal phalanges here. The middle row, that's the intermediate phalanges. And then your toe tips, those are your distal phalanges. Okay, so your heel, this is your calcaneus. Where it articulates with your tibia, this is the talus. Bones in your ankle, these are your tarsal bones. Metatarsals are the bones in your foot. And then proximal row of phalanges, intermediate row of phalanges, distal row of phalanges. All right, and then your shin bone, your tibia. So your tibia will articulate. Remember that word articulate just means to touch. Your tibia articulates with your femur and also with the patella and the fibula, okay? So in your lower leg, you've got the tibia and the fibula. The fibula is lateral to, so to the side of. So if you've got the medial malleolus, remember that's on the inside of your ankle. And then your fibula, that's a long skinny bone that is lateral to the tibia. I'm not going to make you remember all aspects of the fibula. I just want you to know in your lower leg, the larger bone, that's the tibia, that's your shin bone, and the long skinny bone that's lateral to the tibia, that's the fibula. Okay. All right, so the way to side it when you're figuring out this, easiest way to side it is figure out this little bump here, and you have to remember that this little bump is on the inside of your ankle. So this is a left tibia, because this medial malleolus goes on the inside of your ankle here. Okay. All right, so right below your knee, what you're actually feeling that bump is actually your tibia, your tibial tuberosity. And then this ridge, when you hit your shin, that's the anterior ridge here. So you've got the tibial tuberosity and your anterior ridge here. Okay. All right, how are you guys feeling? Is there anything you guys want to go over again? Or are you guys feeling relatively okay?
I feel good. I feel like I just make acronyms for everything and it works out that way.
Yeah. Yeah, and I apologize, guys. I know we're kind of getting to the point in the semester now where it's kind of a bummer that we can't be in the classroom. So I know that, you know, this is all obviously a lot easier to really, you know, learn and cement in your brain if you can actually pick up the bones and feel them and look at them. But I was hoping at least being able to see them here on Zoom. You know, we can continue to do this. You know, I was going to ask you guys too, you know, do you like doing stuff like this more than going over the PowerPoint, or do you appreciate going over the PowerPoint together? Because, you know, my other lab class actually said that they'd rather spend the time on Zoom practicing the bones versus going over PowerPoints. But I wanted to ask you guys as well, what is your preference? Do you prefer?
Well, for me, it kind of depends on the subject matter. Like for the first test, that stuff was more theoretical. Going over the PowerPoint was fine. For this stuff, seeing it makes a big difference. It was much harder reading the book and getting it versus seeing it.
Yeah.
I agree.
Yeah, I mean, we can kind of go topic by topic. I mean, I think we should definitely, you know, next week is going to be forensics. So next week we'll probably spend a little bit of time going over the PowerPoint, and then maybe the last half we'll review the bones again. Because learning the bones, especially the, you know, the aspects I told you guys to really focus on, the skull, the femur, and the aspects of the pelvis, that's going to be important, not just for this unit exam, but every exam going forward. So I think we should definitely at least a few more times make sure that we're really solid really solid with those aspects of the bones and features of the bones. And then when we get to the human evolution sections, I do actually have some of our human ancestors here with us. I have some Australopithecines, and I have, this is Afarensis here. So, I was telling you guys you're going to have to learn about Zygomatic Arch. So when you're looking at this arch here, the zygomatic bone, see how that arch is much more extreme than, when we're looking at the modern human here. So we've got modern human, and then this is an Australopithecine. Other aspects of Australopithecines, see how it sinks in behind the supraorbital ridge. So right here, we've got postorbital constriction. So the reason for that is this is a relatively small brained hominin. Modern Homo sapiens have a cranial capacity within the range of 1,400 to 1,700 cc's, whereas an Australopithecine has a cranial capacity that's very similar to modern day chimps, gorillas, and orangutans. Their cranial capacity for Australopithecines is between 300 to 550 cc's. And the frontal region of their brain is much smaller. So as we progress through human evolution, you're going to see that postorbital constriction reduce. And then eventually with modern humans, it's pretty much absent. The zygomatic arch for the Australopithecines is much more extreme, because what's going through that, this is the opening where the jaw muscles would go through. Okay, so you're seeing that much wider opening because the Australopithecines ate a diet of really rough, tough food items. So they needed really powerful jaw muscles. And also when you're looking at it from the back, it looks a lot different from modern human. The modern human has a much more rounded skull, and the highest, or the widest point I should say, is the parietals up here. And then for the Australopithecine, our widest point is all the way down here at the base, at the occipital region. Okay, so that's some of the features we're going to start looking for. So that's why, I'm just giving you guys a little bit of a preview. That's why it's important that we learn these features now, because in pretty much every lab going forward, it's going to expect that you already know, okay, where is the frontal bone? Where is the supraorbital ridge? Where's the occipital bone? It's going to expect that you already know that stuff. So just so you guys know, learning the stuff in chapter 5 and 6 is going to benefit you the rest of the semester.
I just had a quick question. It's interesting seeing it three-dimensional because I took the class last semester, but is that the sagittal crest on the back? Because I never really understood sagittal crest.
The sagittal crest, oh yeah. Okay, sagittal crest.
Oh, okay.
Is this crest of bone that runs down the sagittal suture. This is Paranthropus boisei. This is a robust Australopithecine. So this is a human ancestor, but as you can see, it looks very different, very robust, very thick. Their zygomatic bones are extremely robust. They've got quite a bit of a zygomatic arch. They have a massive jaw. Look at how huge that jaw is there. Massive jaw. Ramus is huge.
Yeah.
Dentition, the molars. Let me just connect his jaw real quick.
Are all those to scale?
Yes.
Okay.
Yeah, the ones I have here, these are to scale. These are made by a company called Bone Clones. So obviously they're not real fossil material, but they are made from the actual fossils. They made a mold essentially and then used plaster to make it. These are exact replicas of the actual fossils. They are anatomically correct.
But so they have the same dental formula that we do, right?
Yep, so all hominins, so all human ancestors, and actually all of the apes and all of the old world monkeys will also have a 2-1-2-3 dental formula. Only difference is for modern humans, many of us actually need our wisdom teeth removed, that third premolar, because our diet is much softer. If you think about the things that we eat, we use blenders to blend up our food, we use fire to cook our food. So even though we're eating a similar diet, I mean, most hominins are omnivorous, but even though we're eating a relatively similar diet, we're using tool technology and we're using fire to soften our food before we consume it. But boisei, for example, the nickname for this fossil is a nutcracker, because it was originally assumed that this hominin ate very rough, tough food items like nuts. We now know that they likely ate nuts, but they also ate just predominantly vegetation. But if you think about chewing up a salad, so just envision for a second chewing up a salad that has, cucumbers and carrots and, lots of tough veggies. That actually requires a lot more chewing force than if you were to eat a piece of cooked meat or, a piece of, a potato that's been cooked or a carrot that's been cooked. But that's why the robust Australopithecines have these really massive molars. If you look at their molars in comparison to ours, their molars are about 4 times the size of ours. So the sagittal crest, the function of it, the sagittal crest is where the muscles, where the jaw muscles attach. So the jaw muscles will begin all the way here on the ramus, which is part of the mandible. And then they're going to tuck underneath the zygomatic bones. So that's why for these fossils, they have these really wide zygomatic arches. So they tuck underneath. And then they're actually going to connect all the way up here at the sagittal crest. And then for a modern human, our jaw muscles, if you've ever looked at a picture of where our muscles are in comparison, our jaw muscles stop right about here. Because we no longer need those really massive jaw muscles, because our diet, even though it may be relatively similar to our ancestors, it's still omnivorous, meaning a mixture of plants, veggies, fruits, nuts, meat sources. Even though our overall diet is relatively similar, we have tools and we have fire to make our food softer prior to consumption. Is that making sense?
Yeah, I just think it's so interesting how we evolve.
Me too. This is
strong or something,
This is the part I'm very interested to know too. I know from the class that when you were showing up the mandible from the human and from I forget which one this one was, but I know that the old ones were more of a rectangular shape, where the human is more parabolic shape as well, which you can see right there. This is why it's so great to see it rather than looking at it in the book. I wish I was in a class to make it even easier.
Absolutely, yeah. So for a modern human, they call this, it's the shape of the dental arcade. So this is more parabolic, more like a rainbow. And then this one is more U-shaped. So, and I'm trying to get some of the primate skulls for you guys too. I'm working on that. But if you're looking at a chimpanzee, the chimpanzee is more similar to this Australopithecine here. So it's interesting. You're seeing that these, we still, remembering we didn't evolve from the apes, but we do share a common ancestry with them. So it's very interesting to see that some of these earlier hominins, the Australopithecines and Paranthropus, they have a lot of similarities with the apes, more so than they do with us. And they're very, what we call mosaic. They've got some similarities with the apes and some similarities with humans. So, if you've ever heard somebody say that there's no transitional fossils, well, actually there really are. There are a lot of examples of, these fossils that are early on in our human history that are showing aspects of both that make us really understand that, yes, we didn't evolve from the apes, but it's pretty clear we share this common ancestry. At least from an anatomical perspective. We'll talk about behavior as well. We'll talk about, how the behaviors of the apes are similar to the behaviors possibly of early humans. That'll be coming up in chapter 11, I believe. But great questions. You guys have any other questions so far?
Yeah, I have one question.
Okay.
A little curiosity. Have there ever been like any animals that were herbivores before and then mutated into having different teeth and different plants and eventually became omnivores or essentially carnivores?
So herbivores, there are no hominins that are true herbivores. Herbivores are going to have, and again, I wish I had an herbivore jaw here for you, but an herbivore or plant eater is going to have the incisors and then not a whole lot in the middle. And then in the back, they have their molars. So an herbivore, if you think about, even think about for you, if you're going to take a bite out of, a cucumber, for example, a sliced up cucumber, your incisors take off that initial bite. They, do the tearing, and then your premolars and molars do most of the work. They're crushing up the cellulose from that plant. So herbivores have dentition that's adapted to eating just plants. Carnivores have dentition that's almost shaped like a triangle because they're using those triangle-shaped teeth to tear up the meat. Hominins, humans, and chimpanzees, well, chimpanzees are pongoods, but that's something we share in common with the chimpanzees. Our diet is considered mainly omnivorous. So omnivorous diet is eating a mixture of plants, fruits, nuts, meat, But the importance of meat is somewhat overemphasized. It is actually very possible to get enough protein from eating other protein sources like beans and legumes. You don't necessarily have to eat meat to get enough protein. And actually our ancestors, the Australopithecines, it's likely that they ate very little meat. If you look at modern day chimpanzees, they do eat meat, but they don't rely upon it. It's more of kind of a luxury. They eat meat and hunt for meat when they can, but it's not something that they rely on. They definitely eat a lot more vegetation, fruits, insects, nuts. That's the predominant, that's the bulk of their diet. And meat is more of just a every once in a while kind of treat. And that's likely true for the majority of the Australopithecines. You don't really see a huge inclusion of meat in the diet till you get to Homo erectus and onward. So, and we'll talk about this too when we get into chapter 14, 15, 16. You do see this connection once we start consuming more meat, once we start controlling fire, we do see an expansion in our cranial capacity. So it is possible that those two things are correlated, that, once we started including more meat in our diet, that allowed for the eventual expansion of cranial capacity. But a lot of anthropologists really think that the importance of meat has been overemphasized when we're studying human evolution, that it's actually more about fire. That actually, and there's a really great series. It used to be on Netflix. It's called Cooked, I believe. But episode 1 is called Fire. I'll try to find it for you guys and see if it's still free out there. But in that episode, they really talk a lot about how controlling fire really, catapulted human evolution forward, because, it may sound very simple to us, but if you think about it, controlling fire allowed us to cook our food, which can oftentimes extract additional nutrients. It can soften our food and make it easier to digest. Controlling fire allows us to expand into geographical territories that are not warm. We're allowed to now expand into colder regions. If you think about the social benefits of fire, sitting around a fire pit with your friends, after a long day of hunting, if you're thinking about our human ancestors, there's so many benefits to fire. So, in my opinion, I think fire was more important in the grand scheme of human evolution than the inclusion of meat. I mean, of course, meat, allowed us to have another protein source. And we know that in the game of evolution, diversity wins. I mean, the more food sources we have, the better. But I actually think it's likely fire that played a bigger role in comparison to the ability to eat meat. I don't know if that totally answered your question. I'm more of a human, my knowledge is more on humans than it is on herbivores, but I can tell you that an herbivore jaw would look completely different. There would be anterior dentition, there would be a big gap, and then there would be some molars and premolars in the back. Did that answer your question at all, Daniel?
Yeah. It's cool to hear that insight you have. I didn't know that. Very cool. Yeah,
very cool. Yeah, of course. Other questions? Okay, well, that's about all I've got for you guys today. We've been keeping these Zooms at about an hour. Yeah, and I just want to remind you guys, it's a friendly reminder, just make sure you're keeping up on your lab exercises. So at this point, hypothetically, if you're staying on